Assalamu alaikum. In this lecture, we are going to solve the long transmission line model in which we have distributed parameters. In the last few lectures, we have talked about the short, medium, and long transmission line models and also about the ABCD parameters. Now, all the lectures that are from this point onwards will be using the equations that we will derive in today's lecture. To start the derivation, we have considered a small portion of a long transmission line, and we know by the characteristics that any line that has length greater than 250 kilometer, or in miles 150 miles, is termed as a long transmission line, and we usually use distributed parameters rather than lumped parameters in the modeling of that type of lines. From the figure or from the circuit diagram, it is presented there that we have a sending end voltage Vs and the receiving end voltage, and we are only considering a small portion of the line in which we have a capacitor, resistor, and inductance. For the portion of the line that we are considering, the voltage before that segment is Vx plus del x, and the portion length is del x. So we are only considering a small length of the line, and the impedance that consists of resistance and inductance is Z del x, and the current that is passing through the series branch is Ix. For the shunt branch, we have admittance that is represented by small y multiplied by del x, that is the length of the short segment. The sending end current is Is and the receiving end current is IR. Now this Z is the impedance, and it consists of R plus J omega L. This is your inductance, this is your resistance. Similarly, for admittance, we have the formula G plus J omega C. This is your capacitance, and this term is susceptance. This is your conductance. Now, to start the derivation, we are considering this node A as the starting point, and we will be applying KCL and KVL at this particular node. So to calculate the voltage X plus del X, we will apply the KVL at node A. The equation will be del X Vx plus Ix into Z del X. So this voltage Vx plus del X is actually the summation of the voltage Vx plus the voltage drop across this series element. So this is the voltage Vx plus the voltage drop across the impedance Z del X. So this is your KVL equation. So now after rearranging, we will have Ix Z equal to V into X plus del X minus Vx over del X. Now as we know that this del X is a very small distance, so if we consider that del X approaches to 0, which means we are applying a limit on del X that is approaching to 0, then this term will be converted into derivative term, right? So this will be dvx over dx, that is equal to z I x. So this is the first equation that we derived from the KVL application at node A. Now we will apply KCL at node A. And KCL, we will have the equation that is Ix y del x, and the voltage will be X plus del X. So this is the current entering the segment, This is the current leaving the segment, and this is the current of the shunt branch. So this is the current of the shunt branch, this is the current leaving the segment, and this is the current that is entering the segment. So this current is actually the summation of these two currents. This is represented in this equation. Now again, rearranging the equation, we will have the formula that is represented by this fraction, which is equal to Vx plus del x into y. Right? And again, del x is a very small value, so if we apply the limit as the del x is approaching to 0, so this term will be converted into a derivative term. So the differential will be dix over dx equal to y vx. As this del x is approached to 0, so we have y vx, and this term is converted into the derivative. So this is our equation number 2. So now the goal of the derivation is to find the equations for the voltage and current in terms of x, which is actually the distance from the receiving end, and then putting the end conditions, we will calculate the equation in terms of sending end and receiving end voltages as well as the sending end receiving end currents. Now we will take the derivative of equation number 1, and from there we will calculate our first equation that will be for voltage at distance x. So solving one, actually we are taking the differential or derivative of equation number 1 with respect to x. So it will become d square vx over dx z dix over dx. So we have calculated the derivative of current equation, and we will replace this dix over dx with equation number 2. After replacing, we will get the formula, which is d square vx over dx equal to zy vx. Right? So this is the equation that we get after combining equation 1 and 2. Now here in this particular equation, we are having the multiplication of z and y. Z is the impedance per unit length, or the impedance of the line per unit length, and this is the admittance of the line per unit length. And we are assuming that this multiplication of zy can be represented by a constant, that is gamma, and is known as propagation constant. So this gamma square is equal to zy. So gamma will be equal to under root yz. So the equation will be written as dx is equal to gamma square vx, where gamma is the propagation constant, and the value of gamma is equal to under root zy, where z is the impedance per unit length and y is the admittance per unit length. Now the solution of this second order differential equation will be vx is equal to a1 e gamma x plus a2 e minus gamma x. This is our equation B. So before solving this equation and before getting the values for the constant a1 and a2, I'm going to briefly define the gamma constant, which is the propagation constant. and it has two parts. One is alpha, which is the attenuation constant, and the second one is beta, which is the phase constant. So propagation constant itself is a complex number. Alpha is the attenuation constant and it measures the changes in V and I. The changes in the magnitudes of voltage and current per unit length. So what are the changes that are happening in the magnitudes of voltage and current if we are moving from one segment to another? It is being measured by this alpha, which is known as attenuation constant, and the unit of this alpha, this constant, is Nepers per unit length. Similarly, this beta is known as phase constants, and it measures the changes in the phases of the voltage and current. So what is the change in the phase angle between the two segments for the voltage and current? That is being measured by the phase constant, and as it is phase measurement constant, so the unit for the beta is radian per unit length. So this was the explanation for the propagation constant. Now again, we are using the equation number 1 for the voltage that we derived before, which was dVx over dx is equal to Zi into x. And from here, Ix will be equal to 1 over Z d over dx Vx. We have calculated the value of Vx in equation B, and we will put that value in this equation. So the value or the equation for Ix will be equal to 1 over Z d over dx a1e gamma x plus a2 e raised to minus gamma x. So when we will solve this equation, it will be 1 over Z a1e gamma x into gamma minus a2 e minus gamma x into gamma. So we have taken the derivative of the terms. So after solving, we have gamma over Z into a1 e gamma x minus a2 e minus gamma x, and by further solving, zy over z minus gamma x. So the equation for Ix will be under root y over z a1 e gamma x minus a2 e minus gamma x. Now in this equation, this term can be represented in the form of another constant, that is characteristic impedance. And it is represented by Zc, which is equal to the square root of z by y fraction. This is the characteristic impedance. So now we have two equations which are involving the constants a1 and a2, and we want to find the values of these two constants. So we will be solving these two equations in order to get the value of constants, and before that we should know the end conditions. So there are two end conditions that we have to apply. One is for the start of the line, and at the start of the line we have x is equal to L. Just to remind you, x is the distance from the receiving end. So at the start of the line, the distance from the receiving end is actually equal to the length of the line. So that's why I'm saying x is equal to L. And the current at the sending end is equal to Is, and the voltage is Vs. Similarly, for the end of the line, we have the distance from the receiving end equal to 0 because we are at the receiving end. The current I is equal to IR and the voltage is VR. So now using the end condition for the receiving end in equations, we will get the equation VR is equal to A1 plus A2. This is your equation number 1. And for the current equation, IR is equal to 1 over ZC A1 minus A2. This is your equation number 2. So we have replaced Vx value with VR, Ix value with IR, and the value of X is 0. So we replaced e raised to gamma x and e raised to minus gamma x with e raised to 0 and e raised to 0. So this is equal to 1. So therefore we have 1 in multiplication with A1 and A2. Similarly in the equation number 2 as well. So now solving these two equations, we will be getting the values for the constants. 2A1 is equal to VR plus IR ZC and A1 is equal to VR plus IR ZC over 2. Now putting this in equation number 1, VR value will be equal to VR plus IR ZC over 2 plus A2. A2 is equal to 2VR minus VR minus IR ZC over 2, and A2 is equal to VR minus IR ZC over 2. So these are the values for the constant A1 and A2. So now we will put these two constants value in the original values in the original voltage and current equations, which were in the term of Vx and Ix. After putting the constant values in the equation, Vx will be equal to VR plus ZC IR divided by 2 e raised to gamma x plus VR minus ZCIR over 2 e raised to minus gamma x. For Ix, the equation will be VR over ZC plus IR divided by 2 e raised to gamma x minus VR over ZC minus IR divided by 2 e raised to minus gamma x. Now after rearranging the equations, we will get the formulas in terms of cos hyperbolic and sin hyperbolic. For example, for Vx, the formula will be VR into e raised to gamma x plus e raised to minus gamma x divided by 2 plus IR ZC into e raised to gamma x minus e raised to minus gamma x divided by 2. This is your cos hyperbolic x and this is sin hyperbolic x. So the final equation for Vx will be VR cos hyperbolic x cos hyperbolic gamma x, because we have missed this gamma. So this is cos hyperbolic gamma x. Similarly, here we have cos hyperbolic gamma x plus IR ZC sin hyperbolic gamma x. Solving in the same manner, we will get the equation for Ix, that will be equal to VR 1 over ZC sin gamma x plus IR cos hyperbolic gamma x. So these are the equations for the voltage and current in terms of x, and x is representing the distance from the receiving end. So if you have to find at any point in the center of the line or at any distance from the receiving end, you have to find the voltage and current. You have to use these two equations, and the x is representing the distance from the receiving end. But if we have to find the voltages of the sending end, then we have to apply the conditions of the start of the line. And at the start of the line, the conditions were x is equal to L, V is equal to Vs, and I is equal to Is. So this is your Vx and this is your Ix. And after putting these conditions in the equations, we will get the value of Vs is equal to Vr cos hyperbolic gamma L plus IR Zc sine hyperbolic gamma L. Similarly for Is, the equation will be Vr 1 over Zc sine hyperbolic gamma L plus IR cos hyperbolic gamma L. These are the equations for the sending end voltage and sending end current in terms of receiving end voltage and receiving end current. Now we know that from the previous lecture, the term with Vr in the Vs equation is A constant. This is B constant, the term with IR. Similarly for the Is equation, the sending end current equation, the term with Vr is C constant, and the term with IR is D constant. So these are the constants of the long transmission line in terms of propagation constant. Because from the 4-port network representation, we know that Vs is equal to AVR plus BIR, and Is is equal to CVR plus DIR. So A is equal to cos hyperbolic gamma L, B is equal to Zc sine hyperbolic gamma L, C is equal to 1 by Zc sine hyperbolic gamma L, and D is equal to cos hyperbolic gamma L. So we have found out the transmission matrix, which consists of ABCD parameters, and the generic equations for sending end voltage and sending end current for the long transmission line. Thank you.